Okay, so we will start crystal oscillators now. Now we will use transistors in the amplification stage instead of operational amplifier. So we know any oscillator consists of two stages, amplification stage and feedback stage, and it must satisfy Barkhausen criterion conditions. Condition 1 is A beta is equal to 1. Condition 2 is A beta angle is equal to 0 degree or 360 degree. So with that we know. So what is the special property in this crystal oscillator? It uses piezoelectric crystal to generate oscillations. So remember, this is something new. This is a kind of a naturally available crystal. So we know some kind of stones, right? That is a crystal material. So for example, we use quartz, QUARTZ. So we use quartz crystal to generate the oscillations in this crystal oscillator. So it works under the principle of inverse piezoelectric effect. Inverse piezoelectric effect. Okay, so now we will see how this crystal oscillator works. Before that, I think you must know about what is piezoelectric effect, because I said this is working under the principle of inverse piezoelectric effect. So you should know first what is piezoelectric effect. Then I will explain what is inverse piezoelectric effect. If you don't know about this effect, then you cannot really understand crystal oscillator. So let's say many naturally available crystals, naturally it has the property of piezoelectric effect. So this effect is actually, this is a mechanical and electromechanical result. Let us say this is the crystal. This gray color is the some kind of crystal material. So you can take any piezoelectric material. I told you here the example is quartz. So let us say this is a maybe quartz material, and you apply some kind of pressure to this material. So then what will happen? Then this material will produce some kind of very minute voltage or electrical current. So if you if you just measure the voltage across this material, then you can measure some kind of induced voltage. So the electromagnetic field effect, EMFT. So all electrical machines, generators, motors, even the inductors, they all are working based on this electromagnetic field. What is this electromagnetic field? So I'm not sure I should talk about this now, because this is not really part of this course. But generally, we all know about magnet. So magnet, the magnet, two magnet can attract each other. The same pole will repel each other. Opposite poles will attract each other, right? So if you have two magnets, this is the north pole and this is the south pole. And here we have the north pole and we have the south pole. So if you bring these two magnets together very near to each other, then they will repel each other. So they cannot come close to each other because they are same pole. So I have a magnet here in my office. So I will explain this maybe when we have the physical lecture. So this is some kind of magnet, and whenever I bring this magnet near, it attracts, because here in this combination I put the south pole and then the north pole next to each other. Then it's attracting each other. But if I put the same pole, then it will repel each other. Why? Because around each magnet we have the magnetic field, some kind of magnetic field. That's why when you bring it very closer, it automatically attracts or repels. Instead, in electrical engineering, what we are doing, we have some kind of copper wire, copper coil. So in the copper coil, let us say inductor. So in the inductor, when you apply the electricity, or that is the electrical voltage or current. When the current flows, this one also this current is producing some kind of EMF. EMF. EMF means what? Electromagnetic force or electromagnetic field. So this one is same like the magnet. So the magnet have some kind of magnetic field around naturally, but in this inductor or some kind of windings, copper windings, when we apply the electrical current, it will produce some kind of magnetic field. This magnetic field is because of the electricity. That is why we call this as a electromagnetic field. This one is a natural magnetic field, so we call this as a magnetic field, normal magnetic field or natural magnetic field. But this one is because of the electricity, so we call this a electromagnetic field or electromagnetic force. So this is naturally happening, and all the motors and engines and generators, they are really based on this EMFT. So when you come to the third year, I will talk about this EMFT in power electronics when we talk about the drives and so on. So now you should know this. This is electromagnetic field effect or electromagnetic force. So similarly, this quartz material also have certain property. When you apply some kind of pressure, it produces some kind of voltage across its terminals. So this is called piezoelectric effect. So you can see here, you take any piezoelectric material and apply certain pressure on it. So you can see this red arrow mark. And then it will produce voltage across its terminals. So if you just put some kind of voltmeter, then you will really see this needle will move. So you can see some kind of voltage oscillation is happening here. So this effect is called as piezoelectric effect. So now you have some idea what is piezoelectric effect. So what is inverse piezoelectric effect? Because crystal oscillator is working based on the inverse piezoelectric effect. So now we will try to learn what is that. It's just the opposite of this piezoelectric effect. So what I am doing here, so this is the same piezoelectric material. I have the terminal. I take the two wires from this material. I connect this wire or solder this somewhere, and I apply some kind of voltage to this crystal. Then this crystal will start to vibrate automatically. So what it means? So when I apply the voltage, this voltage have certain frequency, right? For example, if I apply the AC voltage with 50 hertz, we know the standard one what we are using in our home is 230 volt AC and 50 hertz. 50 hertz means there will be 50 cycles per second, 50 cycles of frequency per second. Okay, so I apply this to this material, then this material will start to vibrate, or it will oscillate between here and there. So if you measure the frequency of the oscillations in this material, this will be equal to same as this applied voltage frequency. So if I apply 50 hertz, then this will also produce 50 hertz oscillation. So it means it will vibrate 50 times, like very, very fast within a second. So this is called inverse piezoelectric effect. Piezoelectric effect means we apply the pressure to this material and we measure the voltage potential. And in the inverse one, we are applying the voltage and we are measuring this vibration. Okay, so you can take any piezoelectric material, that is the crystal, and apply certain voltage with certain frequency across its terminals here. Then the crystal will also vibrate and produce the same frequency. So whatever the frequency you apply, it will produce the same frequency. This effect is known as inverse piezoelectric effect. So this crystal oscillator is working based on this working principle. Let us say now. So this natural resonant frequency of the crystal is depending upon the thickness of the crystal. So it's not only depending upon the applied voltage, it's also depending upon how thick material you are going to use. So it means the frequency of oscillation is inversely proportional to the thickness of the material or the thickness of the crystal. So if you decrease the thickness of the material, that is a crystal, quartz crystal, for example, then the frequency will increase. So let us say, so if you decrease the thickness, then the frequency will increase. If you increase the thickness, then that's the opposite. Whatever you do increase, the oscillation will be decreased. So that is what I said. Frequency is inversely proportional to 1 divided by T. T is the thickness. So if you decrease the thickness of the crystal, then the frequency will increase. Okay, so mostly we use quartz crystal to generate sinusoidal waves. Reasons are why we are using quartz crystal, because the reasons are it's mechanically strong and it has good piezoelectric sensitivity, and also it's low cost. So crystal is a good choice to generate clock signals. But inside the microprocessor, there are several blocks. We have memories, we have the DMA module, and we have the ALU or arithmetic and logic unit. Inside the arithmetic and logic unit, we have adder, multiplier, divider, subtractor, and so on. So we need to synchronize the operation between all these blocks. For example, adder, if it wants to add some data, A and B, yes, sum is equal to A plus B. So processors are handling all the data in terms of zeros and ones. Zeros and ones. So this is the digital data, bar binary data. Okay. So if this adder want to add this A and B, so it needs to fetch this value from memories, and it needs to process, needs to perform the addition operation, and it needs to send the result yes to another register. Then you are reading that. Okay, so here we need to synchronize. So we need to read this data A from another register R1 and read the data of B from another register R2. So we need to have some kind of synchronization. So we need to have the clock signals. So whenever the clock signal is racing from 0 to 1, the racing edge, I read the data from this R1. And the same racing edge, I am reading the data from this R2. So these kind of clock signals are very, very important in any microcontroller or microprocessor. This is called a master clock or system clock. When you study about microcontroller, you will learn about this. So why I am talking about this here? These clock signals are generated by using these crystal oscillators. So it means inside your microcontroller or microprocessor, you have some kind of oscillators. Mostly we are using these crystal oscillators because it's a cost-effective solution. You can see here it's a low cost. At the same time, it's very strong, mechanically strong, and it has a good piezoelectric sensitivity. So we are producing these clock signals to synchronize different blocks within this microcontroller in order to have an efficient signal processing. Okay, so this is not really our topic. So just forget this. This is just for your information. So we are using this crystal to generate oscillations, and this crystal is working based on this piezoelectric effect. So how can we electrically mention this crystal? So I cannot write this kind of figure when I talk about symbol. So symbol, this is the symbol of the crystal. You just have to remember this is the international standard. If you draw the equivalent circuit of this crystal, this will look like this. So equivalent circuit of the crystal. So we have the R, L, C in series combination. And in parallel, we have another capacitor. So this is the equivalent circuit of the crystal. So let us see what is this R. R is the electrical equivalent of crystal resistance. So each crystal definitely will have some resistance. So this is R is indicating the equivalent resistance of this crystal. L is indicating electrical equivalent inductance of this crystal. This is the inductor, this is the resistor, electrical equivalent resistance and electrical equivalent inductance, and this is the electrical equivalent capacitance of this crystal. And what is the Cm? Cm is the capacitance due to mechanical mounting of the crystal. So if you want to use this crystal, definitely you need to install this on some kind of base. So in that mounting area, there will be some capacitance. So we need to consider all the parameters when we use this crystal to produce oscillations. That's why we are making this kind of equivalent circuit. So Cm is the capacitance due to mechanical mounting of this crystal. So just remember this equivalent circuit. We will use this equivalent circuit in a while. So from the equivalent circuit, we can know that there are two resonance frequencies possible. One is the series resonance frequency, another one is the parallel resonance frequency. So here we have the series resonance frequency, but if you consider here whole, then we have the parallel resonance frequency as well. This is a Fs and this is a Fp, parallel resonance frequency. So we can use this crystal in two different modes, either in series mode or in parallel mode. Okay. At series resonance frequency, impedance of the crystal is very small. So it means the opposition to the current flow is very small. So, but impedance is very high in parallel resonance frequency. So if you just look at this waveform or graph, you can see here, this one is x-axis is the frequency and the y-axis is the impedance, especially output impedance. So due to this capacitive effect, equivalent capacitive effect, because this capacitor is really in this, let us say here. So here we have one capacitor in this series combination. In the parallel combination, we have another Cm, that is this capacitance. So here in the series resonance, the output impedance is really less. But at the same time, when we talk about the parallel resonance, the impedance value is going high. So that is why we have two different frequencies, Fs and Fp. So it's because of this capacitive and inductive effects of the crystal. Okay, now this graph is it's okay to observe, but the more important thing is here now. We have to derive the formula for the series resonance frequency and parallel resonance frequency. So let us see the formula directly now. So Fs is equal to 1 divided by 2 pi square root of Lc. Where this L and C comes from? This is L is the inductance, equivalent inductance of this crystal, but in parallel combination, you must use this formula. So here we have the C and Cm connected in parallel. So the formula is same like this for the parallel, 1 divided by 2 pi square root of Lc. Here C is not just a single capacitor, so we have two different C and Cm. So that is why I wrote the formula like this: C multiplied by Cm divided by C plus Cm. C multiplied by Cm divided by C plus Cm. So the same logic. So this is the formula for parallel resonant frequency of crystal oscillator. So here we don't consider the resistor. So we are considering L and C, inductance value and the capacitance value. So just try to remember, this is something different from what you had seen so far. So usually we had seen only 1 divided by 2 pi RC. But here we are not using RC, or at least we are not using R. So here this is 1 divided by square root of LC, and here is the another formula. So here you can see two different circuits. So one circuit which is based on this series resonance frequency property of the crystal, and here this another circuit, it's based on the parallel resonance frequency property of the crystal. So we already know what is series resonance frequency based on the equivalent circuit and what is the parallel resonance frequency based on this equivalent circuit. So now I am going to use the series resonant frequency effect from this crystal. So I connect this crystal, and this is acting as a feedback stage of my oscillator, that is the crystal oscillator. And I have the amplification stage. Amplification, I am using transistor. So this transistor is a NPN transistor, that you may know that. Why I say this as an NPN transistor, you see the arrow mark is down. So this is a common emitter configuration. So I have the base, this is the base, and I have the collector, this is the collector terminal, and this is the emitter terminal. So in the emitter terminal, I have this RE and CE combination in parallel. In the collector, I have one radio frequency choke. So now here I have used this RF choke, or this is the radio frequency choke, the inductor in this collector. And in the base, I have the feedback. So I take fraction of output from this collector and feeding back to the base again, because this oscillator must need a feedback stage. So this feedback is going through this coupling capacitor CC and crystal, that is the material, quartz material. And we have this R1 and R2. This acts like a potential divider in order to give the biasing stability to this transistor. So remember, potential divider R1 R2, it's mainly for biasing purpose, biasing this transistor. So that is the circuit construction of this series resonance crystal oscillator. Parallel resonance crystal oscillator, then what is the circuit construction? It's kind of similar. So I have also the same common emitter NPN transistor, and I have the base, and I have this emitter also have the same kind of RE and CE, resistor and capacitor, which is in the parallel mode. And also this one, I have this bypass capacitor, or we can say this is a blocking capacitor. This will block the DC components and only allow the AC components. And this is the crystal. The crystal is connected like this, like you can see here, it's in parallel combination. So, and we get this output. So here we are feeding this one from the fraction of output, and then feeding here to this emitter. And then at the same time, you can see here, this is going through this way, the feedback, and then going here, and then going back to base. So we are still giving the feedback to this base, because in any amplifier, we need feedback stage. So here this feedback stage is producing 180-degree phase shift, and the transistor is producing 180-degree phase shift, and the output we get 360-degree phase shift. Okay, so let us see here now. So both circuits are using common emitter voltage divider circuit. Voltage divider, this is the voltage divider R1 and R2, because that is helping us to bias the transistor. In series circuit, crystal is connected as a series element. So here you can see crystal is connected as a series element here in the feedback path. And then in parallel circuit, crystal is connected as a parallel element. Okay. In both circuits, crystal will be operated in inverse piezoelectric effect. So once you turn on the power, then whatever the power has the frequency, then the crystal will start to oscillate. Of course, this transistor will produce some amplification output, and it's also feeding to this crystal, and this, because of this potential, this will start to vibrate, and this vibration, that is the thermal noise, we are just feeding back to this one, and we are getting sustained oscillation at the output. So it means whenever we apply the voltage VCC, then the crystal will vibrate and create some frequency. So in series circuit, since impedance of the crystal is small to the generated frequency, then the amount of amount of feedback to the base is very large. So in series, since the impedance of the crystal is small, so here you can see the impedance. It means impedance is what? That is the some kind of opposition the crystal is providing to the current flow. That is the impedance. That is a kind of resistance. So that will be kind of very less. So it means if this opposition to the current or the resistance is less, then this value, the current flow to this base will be high. So the current flow will to the base will be high. So that is what mentioned here. So the amount of feedback to the base is large. But in parallel circuit, it's the opposite. Crystal will act like an inductor and the circuit will act like Colpitt's oscillator. So this is something new for you now, Colpitt's oscillator. I will explain about the Colpitt's oscillator in a while. So anyway, so just remember this. So here, of course, the feedback path, and we are using this crystal based on the mode you are using this crystal. It's producing different kind of series resonance frequency or parallel resonance frequency, and this will be varying based on the impedance. And the overall purpose, the overall goal of this circuit, either circuit, is producing oscillation at the output. We are done with the crystal oscillator. So crystal oscillator, mainly I want you to remember piezoelectric effect and inverse piezoelectric effect. And after that, we are using this equivalent circuit of the crystal. So based on this, you can observe two different types of frequencies possible. One is the series resonance frequency, another one is the parallel resonance frequency. And these are the formulas. And you can use the crystal in series mode or parallel mode. So we had seen two different circuits. So you can also use this in a series mode and parallel mode. Of course, when you use like this, you have to calculate the resonance frequency using this formula. When you use the crystal here, then you have to use the parallel resonance frequency formula.